Welcome. Today we are going to talk about solving systems of equations. You will recall last week we talked about how to graph a linear equation. Remember, linear equations form lines when they are graphed. Here we see the equation y equals 1/2 x plus 4. In this situation, the 4 at the end of the equation tells us the y-intercept, and we can see by looking at our graph that the line crosses the y-axis at positive 4. You'll also recall the coefficient for the x, which in this case is 1/2, gives us the slope of the line. If we look at this line, it goes up 1 unit for every 2 units it goes over. So the slope of our line is 1/2. When we look at a line, each point on this line makes the equation true. If we look at our y-intercept, the coordinates for the point are 0, 4. If I were to put 0 in for x and 4 in for y, I would have the equation 4 equals 0 plus 4, which is a true equation. It's important to remember that each point on this line makes that equation true when we graph systems of linear equations. So, if we look at a system of equations, and I'm going to go to a file that I have saved, we see a system of equations is two or sometimes more equations that work together. In this case, our first equation, the one we were looking at already, is graphed in pink, and our second equation, y equals 3x minus 1, is graphed in blue. Remember, every point on this pink line makes the first equation true, and every point on the second line makes the second equation true. The only point that is on both lines is this point right here, 2, 5. 2, 5 is the only point that makes both equations true. Therefore, we would say that point 2, 5 is the solution to this system of linear equations. In most cases, like this one, there will be one solution to a system of linear equations. However, there are a couple exceptions to that rule. Let's look at another saved set of equations. In this set, I have two lines. The first, y equals 2/3 x plus 1, and the second, y equals 2/3 x minus 3. You can see both of these lines are graphed on my coordinate plane. However, if I look at the lines, they appear to be parallel, continuing forever without intersecting. If they don't intersect, there cannot be a point that is on both the pink line and on the blue line. When we have parallel lines, we say there is no solution since there is no point where the lines intersect. It is easy to recognize parallel lines when looking at the equations. In this case, both of them have a slope of 2/3. Two parallel lines will always have the same slope. So if you see equations that have the same slope, you know, even without graphing, that the lines will be parallel and that the system has no solution. Let's move on to the third situation. If I look at this line, 2x plus 4y equals 12, I can see that it forms the graph over here to the right. In this case, the line is in standard form instead of slope-intercept form, but we can graph it easily by finding the y-intercept and the x-intercept by first substituting 0 for x to find the y-intercept and then 0 for y to find the x-intercept. Let's say we want to graph a second line. Going back to my saved graphs, you'll see here I have two lines now. I have the line 2x plus 4y equals 12 and the line x plus 2y equals 6. But when I look at my graph, there appears to be only one line. Let's look at what's going on here. I see my blue line, but I'm going to click on it for a minute to make it disappear. Now I see the pink line for 2x plus 4y equals 12 goes through the y-intercept of 3 and the x-intercept of 6. Let me reactivate my blue line. If I do so, my blue line goes through the y-intercept of 3 and the x-intercept of 6 as well. So in reality, both of these equations represent the same line, which is easy to recognize because if I divided each term in the top equation by 2, I would have the bottom equation. This is really two different ways of writing the same equation or representing the same line. But if I look at the points that are on both of these lines, I see there are many points. For example, the point -2, 4 is on the blue line, and it's also on the pink line. The point 0, 3 is on the pink line, and it's also on the blue line. The point 6, 0 is on the blue line, and it's also on the pink line. I could go on for a very long time naming points that are on both lines. In fact, there are infinitely many points that fall on both lines since the line continues forever in two directions. Therefore, anytime we have two equations which produce the same line, we know they have infinitely many solutions. Let's take a minute to review what we learned today. When graphing systems of equations, three possible outcomes can occur. You can have two lines which intersect in one point and therefore have one solution, in this case the point 2, 5. You can have two equations which form parallel lines that never intersect, and we say there is no solution. Finally, you can have two equations that when graphed form the same line. As this is the case, we say that the two equations have infinitely many solutions. Graphing is just one way to solve systems of equations. As we continue through this unit, we will also talk about how to solve systems of equations using substitution and elimination. Which method you prefer is up to you. Sometimes graphing is the easiest way, other times it's not.